Hello guys, my name is Devin, my YouTube channel is Darren's Brothers, and today we're going to be talking about interest. Simple, compound, and continuous. So, first off, we have simple interest. And honestly, that is an easy one to solve. So, for the interest, it's basically that the interest is equal to the starting amount, and then we're going to multiply that by the rate and the amount of time it's in there. So now, A0 is always money in dollars. The rate is always a percentage written as a decimal. So maybe 5%. So 0.05. And then time is always in years. So, using this formula, if someone put $100 into a bank and left it there for 1 year, how much interest would they get, assuming that the rate is 5%? Well, that's actually really easy to solve. The interest they would get would be equal to 100 times 0.05 times 1. And that's 5. Easy enough. But then when we start getting into compound interest, things get a bit more confusing. So, to start this, so compound, the formula for that one is AT equals A0 1 plus RT over N to the N power. And N is the number of compounding. But we're going to come back to that. What I'm going to do is I'm going to simulate how the interest works. So when we have 0 compoundings, that's basically just our money. When we have 1 compounding, that's the same as simple interest. We would have A0, and then because of it's going to be 1 plus RT. And then if we compounded it a second time, that would be our original money times 1 plus RT times 1 plus RT. And that pattern continues for each single compounding. Now we're going to show how we find our formula. So, to do that, we're going to use time over compounding. So we're going to have A1 times the time over the compoundings. And that's almost the same as simple interest. Basically, all we're doing is swapping the t for t over m. So then that's A0 1 plus r t over n. Like that. And then the second one, as we've already shown, we're basically just going to do this again. Now the third, we're going to do that again. But what if we did n? Well, that would be A-n times t over n, which is equal to A0 1 plus r t over m to the n power. And once again, this formula is going to come in handy. But basically, how do we turn this into our simple formula? Well, you'll notice here, these two n's can cancel each other out. So basically, it's just AT is A0 1 plus RT over N to the N power. That's how we got our formula. Okay? And next, we're going to review an actual scenario using compound interest. So using that with the r's and the t's, we get this simple formula, A1 is equal to 1 plus 1 over n. And this is only if our rate is 100%, the time is 1, And it doesn't really matter, although, well, it does matter. It's 1. And so we would turn that into it, because if we use our formula, A1 is equal to 1 times 1 plus 1 times 1 over 1 to the 1 power. If that makes sense. And when that's all done, or over n to the n power. That's how we get this, because this is multiplied. So it's basic, and we can drop this 1. So it's 1 plus 1 over n. And now, we're going to use that to find something very interesting. So, we're going to draw a table here. It's going to be a pretty big table. You'll see why in a minute. So we're going to have on one side n the number of compoundings, and then our formula, 1 plus 1 over n to the n power. And we're going to use this. So 1 compounding, that would be 1 plus 1 over 1 to the 1 power. 1 plus 1 is 2. 2 to the 1 power is 2. Now we're going to do it again. We're going to add a second compounding. And now that's 1 plus a half squared, and that's equal to 2 and a quarter, right? And we're going to keep going. So if we do this 3 times, that's 2.37. 4 times, that's 2.44. Now I'm going to stop here for a moment to show you how the numbers keep increasing. So we've gone from here, adding 0.25. Then we went to here, adding 0.12. And then from here, adding 0.07. Notice how the amount is shrinking in half. Now, technically, these aren't exactly halves, but they are very, very, very close to half. So, now using that, what do you think 10 would be, now knowing that it decreases? 10 is equal to 2.59. It's pretty small. It's a pretty small increase. We've only gone up. Yeah, we only went up 15 from that last jump. What if we went even bigger? What about 100? 100? Again, not much bigger at all. It's only 2.70. That's only a 0.11 increase. And we've gone up at, like, I don't even know the word, whatever, we've over dectupled the amount from here to here, and we got less. And we're about to get even less. What if we went to 1,000? What would that be? Surprisingly, that's only 2.71. We went up 900 places and increased by 0.01 cents, which is not much. So what if we go even further? What about 10,000? Once again, it's a very small increase. 2.71814. And you'll notice here, we can actually write this as a limit. So the limit from n to infinity is 1 plus 1 over m to the n power. That's equal to e. Now, some of you might not know what e is, some might. E is Euler's constant, which has a value of approximately 2.718281828. And it keeps on going. Just like pi, it's an infinite number. An irrational number at that. So, you'll notice, as we keep going, we're actually getting closer and closer to e. I believe the next one, if we did 100,000, I'm pretty sure that's around 2.7182. We get even closer. Now, here's the question. If I kept doing this forever, would I eventually reach E? The answer is yes. although it would take literally forever. But then here's the thing. Each one of these takes a finite number to solve, or a finite amount of time to solve. So in the end, we will never be able to get to E. That's the beauty of this. But now we have a different case. Now we have continuous compound interest. And that's compound, but instead of compounding like twice every month, it compounds every single like second. Like it compounds forever. And so the formula for that is A naught times E, again that's always constant, to the RT power. Alright? Now I'm going to show you the proof for that. We're going to use our compound interest, AT equals the limit of n to infinity, A naught 1 plus RT over n to the n power. And basically, I'm going to solve this through. So, next step, we're going to, here's the next thing we're going to do. Now we're going to add the A naught to our limit. So we have A naught, the limit from n to infinity. We're essentially moving the A naught to the front. 1 plus RT over n to the n power. And now we're going to do something which is known as a variable change. We're going to let m, and that's equal to RTM, and m is just some random number. Now here's the thing. R and t are fixed to 1 and 1. So the only thing that can truly change n is m. And the only thing that can change m is n. If n goes up, if n changes, n changes. Simple as that. So now we're going to essentially do our swapping. So now I have A naught from the limit of m to infinity. And here's where we're going to get some bigger numbers. Now it's going to be 1 plus RT over RTM to the RTM power. But we can cross out these R's and T's. So we're left with A naught from the limit from m to infinity. And then we have 1 plus 1 over m to the RTM power. And now we're going to essentially split the variables. So now you can do this as long as there's no addition or subtraction signs in the variables. So, for example, if we had x to the 2 to the 3 power, we could essentially write that as x squared to the 3rd power, like that. So we're going to use that here. So we're going to do A naught, heavy bracket, the limit from m to infinity, 1 plus 1 over m to the m power, in the bracket, to the RT. And we can even swap the order of the variables. So like in our x example, we could do x cubed squared, essentially. And so, all of this, right here, as we showed in our previous work, because essentially m is n, and here we've shown this is the same as this, just all the m's are n's. So now we can switch all of the m's back to n's, and then it solves to A naught, A to the RT, and there's the proof for that. Thank you very much for watching this video. I hope you enjoyed, and we'll see you for another video. Also, please subscribe. We're hoping for a goal of 20 subscribers, so please subscribe.